Hello, just a quick video here about titration questions at GCSE for GCSE chemistry. This is for triple science only, double award science, you don't need to do this. So titration calculations and titration questions in general, these seem to cause quite a few problems. So in this little video, I'm going to talk a little bit about how a titration is done, not much on that, and then we're going to get straight onto some calculations. So you're going to need a calculator, you're going to need a pen, and you're going to need to not just click through this video hoping for some sort of quick fix. So in the background here, I've got 3 questions to go through, which would be better if you work through these at the same time as me. So this is getting recorded 2025, it's a snow day, so I'm sat at home recording this with snow outside. So I thought I'd do something useful with my time. So I hope it is useful to you. Okay, so I'm going to assume some knowledge here that you know a little bit about what's going on. So in a titration, what we're generally doing is we're going to take an acid and we're going to react it with an alkali. When you react an acid and alkali, you make a salt and you make water. And what we can do, so I'm just got off the screen there a little bit. You make salt plus water. So when an acid and an alkali react, we can do this using some special apparatus called a burette and a pipette. And we can work out, if we know the concentration of the acid, we can work out the concentration of the alkali. And this is pretty much what GCSE titration calculations do. So I'm going to give you an example of this. We're going to take an acid and alkali, so we could take some hydrochloric acid, HCl. We could react it with sodium hydroxide. Hydrochloric acid, sodium chloride. You're going to make sodium chloride, and you're going to make H2O. Okay, so there's an example of the sort of equation that you would get: hydrochloric acid plus sodium hydroxide. Whether or not you're following this so far, the way a titration works is there is always a piece of equipment called a burette. Now, this burette, B-U-R-E-T-T-E, can measure variable volumes of a solution. So you've got a solution in here. This thing represents a tap, so we're going to open this tap, whoop, and then the acid will run out, and then we're going to close the tap when the reaction finishes. So hopefully you've done one of these in class. This is the burette. Normally you put the acid in here, but you can put the alkali in here as well, it wouldn't matter. And then you're going to see this when we look at the questions. There's going to be a conical flask down at the bottom. This is a conical flask, and this contains the other chemical that we're reacting. So for example, you might have an acid in the burette, and you would put the alkali in the conical flask, acid and alkali. You could put it the other way around. The other thing that you will put inside the conical flask to make it colourful or otherwise is an indicator. Alright, so the conical flask will always contain one of the chemicals and an indicator. Right, the final bit of information is normally at GCSE, this conical flask contains 25 centimetres cubed of a chemical, either the acid or the alkali. This number is quite important, and you'll see it again and again when we look at the exam questions. This 25 centimetres cubed has been very, very precisely measured out using a piece of equipment that looks like this, and hopefully you've used one of these in school as well. Alright, this piece of equipment is called a pipette. Oops, not a pipette. Also known as a volumetric pipette. And this piece of equipment here has got one job. And its one job is to measure out 25.00 centimetres cubed of solution. So the burette measures various different volumes very precisely, but a volumetric pipette measures 25.00. It measures one volume very precisely. So what we're going to do, this is going to take a solution and that's going to go into there. So we use a pipette to put 25 centimetres cubed of solution into this conical flask. And a burette has got another solution in that is going to react with the stuff in the conical flask. So you're probably aware of this. So we've got our burette full of acid, maybe we've got some alkali with an indicator, and what we're going to do is we're going to open this tap, open the tap, and little drips will go in there, and we will run the experiment until the indicator changes colour. Okay, you all ready with that? You're fine with that? So hopefully that's just setting the scene. So we've got an acid in a burette. We open the tap, drip, 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 drip. You wait for the indicator to change colour. We can call that the end point. And then from that information, we're going to have to do some calculations. So that's just setting the scene. You might not have learnt much so far, but we're going to see when you get into the questions, this is going to be quite useful information. There will always be a burette. There will always be a conical flask. They will always have 25 centimetres cubed of solution. All right, so you may well be watching this video going, that wasn't very good, I don't know very much yet. Well, we're going to get on to calculations very soon, and you're going to see why this is an important little diagram. All right, the next thing to know then, I'm going to just draw up an equation, same one as before. We're going to have hydrochloric acid, and we're going to have sodium hydroxide, and they're going to be making sodium chloride plus water. So this is an equation, it's a simple equation. What this tells me, there are no big numbers in front of these chemicals. So what this tells me is one of these reacts with one of these. All right. So if I know that one of these reacts with one of these, I know that 1 dozen of these reacts with 1 dozen of these. And therefore, I know that 1 mole of these reacts with 1 mole of these. This is our molar ratio. 1 mole reacts with 1 mole. Now then, an important thing here is when we're dealing with solutions, to work out the number of moles of a solution, the number of moles is the concentration times the volume of that solution. There's a little key thing that is very useful at GCSE. The concentration is given in moles per decimeters cubed, and the volume is nearly always given in centimeters cubed. So what I teach my classes is this quite a useful little system where instead of learning moles equals C times V, we learn moles equals CV divided by 1000. If you're watching this and you don't go to my school, this is quite a useful little summary. Moles equals the concentration in moles per decimeter cubed times the volume, all divided by 1000. So I'm going to be saying through this video, moles equals CV divided by 1000. Okay. So what this means is, if you're given the concentration and the volume of a chemical, you can work out how many moles. So let's go to this little example here, and then as soon as we see some worked examples, I promise you this will help. So if you have, so when we've got two solutions reacting together, I promise you in GCSE you will be given a C and a V of one, and you've got to work out a C and a V of another. So you've got C's and V's. So what I like to do, sorry, I'm going to clarify in a second, is we're going to look for concentrations and volumes of each of these chemicals. The general thing is going to be, when you read these questions, you will be given the concentration and the volume of one of the chemicals, and you will typically be given the volume of another. And what you will have to do is work out the missing C or V. So if you see here, there are 4 things I need, C, V, C, V. And you're typically given a C, a V, and a V, and you've got to work out the missing C. That's typically. So what we would do, if you've got a C and a V, you can see from my calculation here, we can work out moles. So what we're going to do, we're going to use this, whichever C and V we've got, we're going to work out the moles by doing C times V divided by 1000. If I know that the number of moles of this, and I know that from this ratio, 1 mole reacts with 1 mole, I'm going to put the little ratio on here. If I've got a C and a V, I can work out moles of this substance. If I know the moles of this substance, and I know that 1 mole reacts with 1 mole, I will know the moles of this substance. So therefore, if I've got the moles of this and the V, okay, this is the clever bit. If I know that moles equals C times V over 1000, I can rearrange this to work out C. So C equals, I'm going to do moles times 1000, moles times 1000 divided by the volume. So all I've got here, I've got moles and a volume, so I could do C equals moles times 1000 divided by the volume. And this will give you your missing answer. All right. In theory, Maybe you're following that, maybe you're not. I promise you, by the third question, this will be a revelation to you. You'll be like, oh my gosh, why was this so hard in class? Right then, so this is our general plan. Let me sort out this general plan for you again. In your exam, you are going to be given an equation where you've got something reacting with something. You're going to collect C's and V's. You will probably get something that looks like that. A C, a V, and a V. You're going to go down from the C and the V, you're going to go across, and you're going to go up. This across arrow is going to be a ratio. It might be 1 to 1, you'll see in a minute. It might be 2 to 1, it might be 1 to 2, whatever. It's going to be a ratio. We're going to go CV divided by 1,000. That will get us our first mark. We're then going to use a ratio. That will get us our second mark. And on this side, we're going to do moles times 1,000 divided by V. All right, that's it. If you had this combination, something plus something, you're going to collect C's and V's. Watch this. If you've got a C and a V and a C, and you've got to work out the missing one here, we're going to go down, we're going to go across, and we're going to go up. The ratio is the big number ratio from the equation from up here. So again, it might be 1 to 1, it might be 2 to 1, whatever it might be. We're going to go CV over 1,000. That's our first move. We're going to work out this. If we know 2 of this, we'll know 1 of this. We're going to go here, and then we're going to go moles times 1,000 divided by, in this case, C. That will give us our answer. All right. If you followed that, great. If you didn't, we're on to some worked examples now. So you'll get it in a minute. Let's have a look at some questions using this sort of approach. Right. So, hopefully, you're roughly following, but now you're going to see some of these questions in action. I'm going to go, firstly, I've got June 2020. It says here, they've got a titration. Measure 25 of sodium hydroxide into a conical flask using a pipette. All right, then, so I'm just going to draw this out. They've got 25 into a conical flask, and they've used a pipette, just like I've said. So that pipette's gone into there. They've added some indicator to the flask. Indicators in there as well. Sorry about the bad writing. And then they're going to fill a burette with citric acid solution. All right, I'm drawing this because it makes it clearer what's going on. I've got sodium hydroxide. Sodium hydroxide is in here with an indicator, and they've got citric acid in a burette. So I've read this, and I've read this. Describe how the student would complete the titration. So they're going to open the tap on the burette. They're going to run some citric acid into the sodium hydroxide until you get a colour change. All right, so you're going to get a colour change at the end point. Then you would repeat the experiment to find concordant results. We're going to come to that in a minute. Concordant results. All right, so let's have a little look at the page, how they did it. Give 2 reasons why a burette is used for the citric acid solution. It can measure variable volumes. It can measure them very precisely. I'm just going to check the answers. So small increments. All right, so I didn't quite get that right. Small increments, variable volumes. I said very precisely, so it can add it drop by drop and variable volumes. All right, let's get on to the calculation. So I said that whenever you get a titration calculation, this technique will work. I'm going to collect C's and V's. All right. If I've got C's and V's, I can do this very, very quickly. So what I've got here is I've got 3 NaOH. Look at what I do first. I'm going to rewrite the equation because I want it bigger so I can put my working around it. And I'm going to look for C's and V's. Before I even look at the calculation, I know I'm going to go from one of these across and up. So actually, I'm going to read the question first. So I've got 13.3 centimeters cubed of a 0.5 mole per decimeter cubed citric acid solution. All right, this is sodium hydroxide, so this must be citric acid. I've got 13.3 centimeters cubed, that's a volume, 13.3 of a 0.05 mole per decimeter cubed, so that's a C. It was needed to neutralise 25 centimeters cubed of sodium hydroxide, so that's a V. All right, I'm going to put that in here, 25 centimeters cubed. And notice what we've got. We've got this one missing. The equation is this. Calculate the concentration. Cool. All right, I've got a C and a V, and I've got a missing one here. So What I've got here then, the C and the V is on this side, so I'm going to go down from there because I can work out my moles. I'm going to go across with a ratio, and then I'm going to pop up here. Notice I haven't got my calculator out yet. All right, so I'm going to do C times V divided by 1,000. That's going to get me this. The ratio. There's one of these for every 3 of these. So I'm going to write 1 to 3. So if this is number 1, this is number 3. And then to come up, I'm going to do moles times 1,000 divided by, well, I've got V, and that will give me C. To make it so I definitely get the marks, I'm going to write the equation out in full. I'm going to do 0.05 times 13.3 divided by 1,000. I'm going to do that now. Okay, calculator's coming out finally. So all I've got to do is follow my little plan. 0.05 times 13.3, funny calculator this, equals, divided by 1,000 equals. Now then, how'd you get the other answer on here? Format. That ain't right. Pause for a sec, ask my daughter. Right, after a brief interlude, I just asked my daughter how to use her calculator. 0.05 times 13.3 equals, divided by 1,000 equals, then you go format, as you were probably all telling me. 0.0000665, and I'm going to write the word moles there so my examiner knows what I've just worked out. I've just worked out moles by doing CV over 1,000. I've just got a mark in my GCSE. Well done, me. If this is 1, then this is 3. So what I'm going to do is I'm going to take this number and times it by 3. So it's sat on my calculator. Look, my ratio tells me if this is 1, this is 3. So I'm just going to times that by 3. Great, this is really not a very intuitive thing, is it? 0.001995, 0.001995 moles. So I've just worked out the moles of sodium hydroxide. It's directly below there. If I take this number, times it by 1,000, and then divide it by 25, so I'm going to write that in, 0.001995 times 1,000 divided by 25. So the number's here, I'm going to times it by 1,000 equals, divided by 25 equals, format, decimal, 0.0798, 0.0798. Concentration is there, so I'm going to write it on the line, 0.0798 moles per decimeter cubed. Make that clear for the examiner. Let me get the answers out, sorry. Let me get the answers out. Where are you? I know this has been a bit scrappy, but I haven't rehearsed it, obviously. Alright, firstly, Bosch, 0.0798. I'm going to get a mark for that. Mark. Alright. Moles of citric acid, 0.000665. 0.000665, 1 mark. Times it by 3, 0.001995, 1 mark. Correct answer, 1 mark. Alright, notice what I did. I collected C's and V's. Whichever one I had both of, I went down. Then I went across, then I went up. Let's do the next one. Alright. I'll try not to make any mistakes on the other questions, because that's not very good, is it? I'm warming up a bit now. Now I've actually got into some questions. This is 2022. I'm not doing strong and weak acids today. I'm doing this. Now this is a titration question with a results table. Alright, and I'm going to come back to this word concordant in a second. Concordant. Okay, let me read the question and get everything drawn out in a picture. A student titrated, there's that magic number, 25 centimetres cubed of hydrochloric acid with 0.1 of barium hydroxide solution. The 25 means that it's in here. I've got hydrochloric acid, oops, can't see there, hydrochloric acid in here, there's 25.00. I promise you that number, it goes in the conical flask. Then they're going to have a burette over the top, and in here is the barium hydroxide. I'm just going to use the formula. You don't necessarily need the formula. It'll come up in a minute. That's barium hydroxide, and this is 0.1 moles per decimeter cubed. Moles per decimeter cubed. All right, so I've got my setup. They've got some acid in here, 25 of acid in there. They've got an alkali here, barium hydroxide. They're going to have an indicator in there as well. So what they're going to do in this experiment is they're going to open up this tap for the barium hydroxide. It's going to run in, the indicator will change colour, and they'll record the volume of barium hydroxide that went in. Now this is what they often do in a titration question. This student repeated the experiment 1, 2, 3, 4. They did 5 experiments. In the first experiment, they needed this much barium hydroxide, then this much, then this much, then this much, then this much. What you're expected to do at GCSE is you're expected to know when you've got results here, you are looking for concordant results. Concordant results are within 0.1 centimetres cubed of each other. Once we have concordant results, we are going to take the average of the concordant results. So our first job is to get rid of any anomalous results. All right. So I'm looking for anything that is in 0.1 of each other. 23.55, 23.55, they're concordant. 23.45, 23.45. These are all within 0.1 of each other, these 4. This one is well out, boop, boop, so we don't include it. The student calculated the volume of barium hydroxide solution to be used in the titration calculation as 23.50. Explain why the student used the volume of 23.50 in the titration calculation. What they did, the student did not use the anomalous result from titration 1. They took the average, or the mean, I'm going to use the word mean, of the concordant results, which was 23.45 plus 23.45 plus 23.55 plus 23.55 divided by 4, and that gives you the answer 23.50. So they didn't use the anomalous results, and they took the mean of the concordant results. Next, let's look at the question. All right, here's the titration question. This is probably why you want to watch this video. You're here just for this, I suppose. Okay, here's an equation, titration calculation worth 4 marks. So, it's a titration calculation. Watch my first move. BaOH2. I'm not really interested in the products. I'm just interested in how these react. 2 of these reacts with 1 of these. 2 of these reacts with 1 of these. I'm going to collect C's and V's. 25 of the hydrochloric acid, that's a volume, 25. Reacted with 23.5 of the barium hydroxide solution. 23.5, that's a volume. We're going to write that in there. 23.50, that's the barium hydroxide. This number, that's a concentration, 0.1, I can tell from the units. So as you see, I've got 1, 2, 3 things, and I'm missing the 4th. Calculate the concentration of the hydrochloric acid. Good, that's my missing number. So notice what I'm going to do. I've got a C and a V, so I'm going to go down, I'm going to go across, and I'm going to go up. All right, I'm going to go CV divided by 1,000. I've then got a ratio. One of those reacts with 2 of these, 1 to 2. I'm then going to do moles times 1,000 divided by V, and that'll give me my concentration. All right. 0.1 times 23.5 divided by 1,000. Then I'm going to get my calculator out. Right. 0.1 times 23.5 equals divided by 1,000 equals format. Down there. Bosh. 0.00235 moles. I've got a marker. Now I have. If one of these, this is 1, this is 2, so I'm going to times this by 2. Times 2. Haven't pressed clear on my calculator. I'm just keeping it all on there. 0.0047, 0.0047. Next job then, moles times 1,000. 0.0047 times 1,000 divided by 25. I would write this in so the examiner knows what you've done. Okay, what is it? Times 1,000 divided by 25. Oops. Press the stupid button. Start again, Norton. I'm going to start right over here. 0.1 times 23.5 equals divided by 1,000 equals times 2 equals, and I'm back where I was. Let's try and not, so I'm here again. Okay, times 1,000 times 1,000 equals divided by 25 equals format down, decimal, 0.188, 0.188. Calculate the concentration in moles per decimeter cubed, 0.188. I'm just going to check for significant figures or anything. No, that looks all right to me. Let's have a little look. Question 8.3. Question 8.3. So, moles of barium hydroxide, 0.00235, 0.00235, 1 mark. Times that by 2 for your second mark, times that by 2 for your second mark. Answer 0.188. Okay, this sum has to be written in. Moles times 1,000 divided by 25. Moles times 1,000 divided by 25. Answer 0.1884. Easy marks. Alright, so again, what are we doing? You're going to get an equation. It's going to have something and something. It's going to have a ratio. We're going to go down, we're going to go across, we're going to go up. We're going to do CV over 1,000. We're going to use a ratio. We're going to do moles times 1,000 divided by C or divided by V, whatever happens. You might also go down, across and up. It doesn't matter. Let's look at the final example then. Hopefully you're still with me. Should have 3 questions here. 8.3. Alright, done that one, done that one, done that one. And I have one more question here. Okay. A student does a titration using sodium carbonate solution and nitric acid. Here's an equation. The equation for the reaction is this. That means one of these reacts with 2 of these. Let me get my head around what they're doing. 25 centimeters cubed, cool, I've got that, of this concentration sodium carbonate is neutralized by this much acid. Alright, so you don't need to do this, I suppose, but there's my 25. This is 25 centimeters cubed of 0.124, and this is sodium carbonate, which I can see from the equation is Na2CO3. There's the magic 25 number, and it's neutralized by nitric acid, so it sounds to me like the nitric acid is in there, and they've given me a volume of that, 23.6. Okay. Calculate the concentration of nitric acid. I think I can do that. Give your answer to 3 sig figs. Interesting. Wow, 5 marks. You should calculate the number of moles of this, the number of moles is, and the concentration. That's just telling you to do what we've been doing anyway. First move, 1 Na2CO3 plus 2 HNO3. One of these reacts with 2 of these. I can't be bothered with the rest of the equation. It's not relevant. I'm going to collect C's and V's, C's and V's, C's and V's. 25 of 0.124 sodium carbonate. 25 0.124 of sodium carbonate. Okay, I've collected a V and a C. It's neutralized by this much acid, 23.6. 23.6. I'm missing a concentration. Alright, I'm going to go down, I'm going to go across, and I'm going to go up. I'm going to do CV divided by 1,000. I'm going to do a ratio 1 to 2, and I'm going to do moles times 1,000 divided by V. Alright, 0.124 times 25 divided by 1,000. Okay, getting a bit fast now. Let's get going. 0.124 times 25 equals divided by 1000 equals. Alright, write that in here. Format decimal there. What have I got? 0.0031. 0.0031 moles. This means times by 2. This is 1, this is 2. So I'm just going to press times by 2. Times by 2 equals. Format standard decimal. This is so irritating. 0.0062. 0.0062 moles. Now I've got to do moles times 1,000 divided by V. So I'm going to go 0.0062 times 1,000 divided by V is 23.6. So I'm going to do times 1,000 equals divided by 23.6 equals format decimal 0.2627. 0.2627 moles per decimeter cubed. Right. Concentration to 3 sig figs. 0.263. 0.263. I think I'm done. Right. Right, firstly, 0.263. So I've got that mark. That means I've got all the others right. Okay, promise you. That was it. 3 calculations using that method, down, across and up. I've got about 30 seconds just to do something else. Just for a bonus, so they're the calculations. Just be aware then, other things that I've not really gone into much detail. I talked a little bit about concordant results. That means you repeat an experiment and you get them within 0.1 centimetres cubed of each other, and we ignore non-concordant results. We take an average of the concordant results, or a mean of the concordant results. In other words, you ignore any dodgy results that are more than 0.1 out. Let's just read this question. The concentration of an acid can be determined by a titration. An indicator is added. Name an indicator. Okay, not a lot of people know that you need to know the names of indicators. The one I tend to get people to know is this. Phenol. I'm going to go into a separate line. Phthalene. Phenol, phthalene. All right, another way, because it's just been Christmas. Phenolph, like Rudolph. Phthalene. Phenolph, phthalene, like Rudolph, phthalene. All right, they will give you a little bit of wiggle room with the spelling. All right, then. Phenolphthalein is pink in alkali. Give the colour change of the indicator when acid from the burette is added to the alkali in the flask. So if you already got alkali in the flask, it will already be pink. And when you add acid to it, it will turn colourless. So it'll go from pink in alkali to colourless when the acid has neutralised it, because it tells you here an indicator is added to an alkali in a flask. Phenolphthalein is pink in alkali. Weak acid, only partially ionised in solution. There's loads of bits on here. Solution of an ion that makes the solution alkaline is always OH minus. If they asked you this question, give the formula of an ion that makes the solution acidic, the answer would be H+. Alright, so just a little bit of bonus revision there. I know that was a bit scrappy, but I'm a sort of a one-take kind of person, and I warmed up going through it. I hope if you just look at those 3 worked examples, you will see that there is a very, very simple approach to these. So if you get a titration question in the exam, what you're going to do is you're going to write down the equation. For example, this H2SO4 plus 2NaOH. You would write that down. You would then collect C's and V's, and you would probably be given a C, a V, and a V, and work out the missing C. You then get, wherever you've got a C and a V, you're going to go down, then you're going to go across, then you're going to go up. You're going to put the ratio on this arrow, so in this case 1 to 2. You're going to do CV over 1,000 there to get you this mark, and then you're going to go moles times 1,000 divided by V to get you this mark. Good luck. I hope that was fairly useful. I'll probably re-record this in the future when I'm a little bit more clear-headed. All right, bye.